the course on medical biomaterials. Hello everyone, we will continue on the historical perspective of biomaterials. As I mentioned in the previous class, we have biomaterials made up of synthetic materials, it could be metals, it could be polymers, it could be ceramics, it could be semiconductor material, and there could be blends of all these. In addition, we also have natural materials. Nowadays quite a lot of interest is being shown on natural biopolymers which are produced by bacteria or from the plant source. So let us look at history of biomaterials. This dates back to almost 2000 or even 3000 years back. The Chinese, the Romans, the Indians used gold, silver and mercury in dentistry. They used to have different type of teeth, even wood teeth, ivory teeth and so on actually, okay. And then aseptic surgery was even practiced almost about 120-50 years back, and after a fracture even bone plates were implanted as early as 1900, okay. Then in the year of 20th century AD, synthetic polymers were started being used in biomaterials, okay. Then polymethyl methacrylate was getting popular, one of the most popular polymers because it was used in the World War II, and hence they were also used in biomaterials. Another material another polymer which was very popular was polyester, because polyester was used in many industrial applications as well as in everyday clothing. So that also went into the biomaterials. Then in the 60s, polyethylene started coming into, sometimes combination of metals coated with polymers, so that especially in hip joints one could have better flow properties, one could have better moving properties especially in the joints, okay. So the biomaterial could be thought of as 4 stages or 4 generations. The very early biomaterial, the general feeling was the material has to be inert, it should not cause any adverse reaction to the host, that is all. So the whole goal was looking at material which were completely inert. The second generation of biomaterials was that material should be active, that means the host system should be able to respond to the material and the material should be conducive to the host system. So the second generation of biomaterials which came around 80s were thought of in terms of bioactivity. The third generation of biomaterial looking at regenerating functional tissues, okay, that was the third generation of biomaterials using nanocomposites, nanomaterials and so on. And the fourth generation of biomaterials, they started thinking in terms of tissue engineering, that means can I make different types of tissues outside in the lab and bring it in and use it inside, okay. Can the tissues grow or cells grow on top of these biomaterials without differentiating as a foreign body. So that is how the evolution of biomaterials started, and that is how the thinking with respect to the biomaterials usage and research also started actually. So if you look at this particular figure, it nicely gives you an idea. So the first generation I would say of biomaterials, we are talking in terms of inert materials. The second generation of bioactive materials, bioresorbable, that means material which will completely dissolve or get absorbed, and the third was bioactive and bioresorbable biomaterials involving nanocomposites and hybrid materials, okay. The fourth was biomimetic biomaterials, that means like engineered scaffolds and so on. That is how the biomaterials started coming, and as you can see it is hardly 80-year-old research. It started from 1950s going right up to 2020s and 30s, although biomaterial was used, as I showed you in the previous slide, as old as Chinese and Indians and Romans, but that was more of an ad hoc and it was just practiced. So in the first generation of biomaterials, they were talking about stainless steel, okay, titanium alloys and so on, which was very inert. it never caused any adverse reaction to the host. The second generation, they started using bioceramics, they started using polymeric material, hydroxyapatite, okay, then polymers like polycaprolactone, then polylactic acid, collagen, polylactic glycolic acid, and so on. Okay. The third generation involved a lot of nanocomposites. It was hybrid combinations of polymers and metals, combinations of ceramics and metals, and so on actually, right. So, hydroxyapatite, polylactic acid, and so on. The fourth generation, where we want tissues to grow on the material so that it does not differentiate whether it is the host natural system or a synthetic system. So, we had nanohydroxyapatite, collagen, cellular biological molecules like proteins, okay, immunomodulators, okay, growth factors. So, the tissues started growing on that. Okay. So, a lot of research is being done on tissue engineering, developing scaffolds which will allow tissues to grow, differentiate, and then the scaffold may completely get absorbed. So, the scaffold will completely disappear. So, this is the historical perspective of biomaterial, I would say, over the past 80 to 100 years. Okay. So, the first generation ad hoc implants. So, the physicians used common material which are found around them or borrowed materials from engineering disciplines. So, it was more like accidental rather than design, like gold fillings like mercury or silver, wooden teeth, polymethyl methacrylate. So, a lot of these natural materials were used, glass eyes when the eyes got destroyed due to accident or due to growth. Dacron like polyesters, parachute cloth, they were all used in vascular implants. So, they are more of accident rather than by design. Okay. If you go to second generation, it is engineered. So, there is a collaboration between the physician and the medical practitioner. So, the medical practitioner would say what type of materials are desired. So, the physician the engineers would modify certain structures so that we get the properties. So, there was a lot of advanced material science research being done, like use of titanium alloy, orthopedic implants, cobalt, chromium, molybdenum type of orthopedic implants, ultra high molecular weight polyethylene surfaces, heart valves. So, all these came under the second generation, where there was a lot of collaboration between the physicians and the engineers. For example, if you look at this heart valve, okay, so it has got a titanium cobalt alloy, and then ring here, titanium cobalt alloy, and here you have a terephthalate and PTFE, polytetrafluoroethylene. So, it is a combination of two materials, and they were all engineered so that they will do their purpose. Or if you look at pure titanium cages, these are used for long bone segmental defect. So, if the bones have defects more than 2 inches, then you can't just hope that it will cure by itself. So, they have to do some other ways, and these are called long bone segmental defect, and titanium cages are used to address this type of long bone segmental defect. If you look at this is a polytetrafluoroethylene vascular graft. These are small diameter vascular grafts. If the that is about 1 mm or something like that, 1.5 mm. If you had 2 mm or 2.5 mm, we can use PTFE, or we can use even polyesters. PTFEs are very inert, and they can also be nicely designed for diameter of interest. Okay. Now, if you look at third generation, they are bioengineered implants using bioengineered materials like nanocomposites, like using nano oxides, nanopolymers in drug delivery. Okay, they releases the drug in the nanoscale material, and then it gets completely biodegraded. Or novel blends like combination of synthetic and biopolymers, or metal and polymers, metal and biopolymers. So, combinations of many of these. These are very much engineered and bioengineered materials. Okay. So, they are mostly nanoscale, so they had good interaction with the host system. When you go to the fourth generation, the general feeling is to have biomimetic material. This is an important word you will come across in biomaterials. Biomimetic, it is designed with specific structure and function mimicking the biological molecules. Okay. So, in the human system you are supposed to be having proteins, you have many enzymes, you have peptides, growth factors. So, the biomaterial you are designing should be mimicking these complex biological molecules, and they should provide the structure function infrastructure. They act as a matrix or a base for the cells to grow. They also get involved in biological signaling. That means you sometimes include signaling molecules which are slowly released, inflammatory molecules which are slowly released, so that certain actions take place. Okay. So, you can help in delivering proteins, you can use it for gene therapy, you can use it for drug delivery and so on actually. So, 4th generation biomaterials are of recent origin, and I think the biomaterial research is going in that direction. These are tissue engineered implants designed to regrow rather than replace tissues. Artificial skins being looked at by this particular company, looking at cell cartilage procedure, looking at bone repair cements, they are resorbable bone repair cement. Okay. Genetically engineered biological components are being researched by these companies. So, these are called the 4th generation biomaterials. They are biomimetics, that means they mimic the actual body part, either in the form of acting as support or acting as a matrix for the cells to grow, sometimes giving out biological signals, sometimes giving out proteins, genes, drugs and so on. And finally, it may completely bioresorb and disappear. Okay. These are called the 4th generation biomaterials. Okay. If you look at polymeric biomaterials, many polymers are used as biomaterials, and many of them are approved by the FDA: polymethyl methacrylate, polyvinyl PVC, polyvinyl chloride, PLA, polylactic acid, polyglycolic acid, PE, polyester, PP, polypropylene, PA, polyacetate, polytetrafluoroethylene, polyester, okay, polyurethane, silicones. All these are biomaterials which are used in different parts of the body, and many of them have been approved by the FDA. What are the advantages? They are easy to make, even complicated items could be made. We can make it so that we can tailor the physical and mechanical properties. So, I want a very soft material, I can use a polymer. I want to have a very hard material, I want to have a very strong material like polycarbonate. So, we can nicely tailor. We can do nice surface modification so that the material is biocompatible with the host system, the material does not cause adverse reaction with the plasma proteins. We can help the material as a scaffold for immobilizing cells. It can be made biodegradable. If you want to have a biodegradable drug delivery system, or if you want to have a biodegradable scaffold, you have to go for polymeric material. But what are the disadvantages? Leachable. Sometimes the unreacted monomers may leach out. Sometimes if it is a blend of 2-3 polymers, some polymers may leach out, which may be toxic. Okay. There is you might be knowing polycarbonate is made up of bisphenol A and diphenyl carbonate, and sometimes this bisphenol A leaches out, which is known to have an endocrine disordering property. So, there is a worry about polycarbonate. If you take polymethyl methacrylate, which is widely used in dental, acrylic acid, which may be in the order of ppm or even very much smaller than that, may be leaching out very slowly, which could be toxic. So, that is one disadvantage. They can absorb water and proteins, and sometimes it is taken as advantage, sometimes it is taken as a disadvantage, because they may absorb and they may swell, which is good in some way because it has the water carrying purpose. Sometimes surface contamination can happen while handling oil or other material contamination. They can wear easily, unlike metals. They can break down because of UV or other gamma rays. They can biodegrade, which is an advantage as well as which is disadvantage. Suppose I am using a ultra high molecular weight polyethylene in joints, I do not want it to biodegrade. whereas if I am using a stent, biodegradable stent, I want to degrade. So, this is advantage as well as disadvantage. Difficult to sterilize. There are different sterilization procedures which have to be adopted before the material is placed inside the body. Some polymers cannot withstand certain conditions. So, we will talk about it later as time goes on. Ceramics, they are oxides like alumina, zirconia, silicate glass, calcium phosphate, calcium carbonate, calcium sulphate, they hydroxyapatite. So, there is a lot of interest in ceramics because many of our body like bone contain a lot of hydroxyapatite. So, they are extremely biocompatible and they are bioresorbable. So, there is a lot of interest in bioceramics. Disadvantage and advantages are there. Ceramics high compression strength, they have good wear and corrosion resistance, can be polished, they are very bioactive and bioinert. So, the advantage is the system easily adapts, the host system easily adapts to this. They have high modulus, so they do not match with the bone, they do not have any tensile tension, so they easily snap. So, we cannot use it in such situations. They have low fracture toughness, it is difficult to fabricate, so you have to be very, very careful about when you are designing. So, it has got some advantages and disadvantages. Metallic biomaterials, stainless steel 316, cobalt chromium, titanium aluminum, silver, gold, copper, palladium alloys, amalgam, all of them with different amounts of mercury, nickel, titanium. So, a lot of metals are being used as biomaterials nowadays in different parts of the body. High strength, good fatigue resistance, good wear resistance, easy fabrication. We can fabricate nicely and the technology for metals has been there for almost 200 years. So, that is the advantage. Easy to sterilize, we can heat it up to very high temperature and bring it down. So, nothing will happen to metals. Shape memory, we can even design material which retains its original shape. These are advantages. High modulus is a big problem. These materials are very strong. So, if I am going to use it in place of a bone, when you compare the strength, modulus strength of the bone and the metal, there is a mismatch. Corrosion is a problem because stainless steel can get corroded over a long period of time, many metals can get corroded. Metal ion sensitivity and toxicity, slow leaching of metals is a big problem, even if it could be in the order of a part per billion, some patients may be allergic to metal toxicity. Metallic looking, you will always, suppose I put metals in the teeth, in the oral cavity, then the metal look does not is not very aesthetic. So, there we may have to go to polymeric type of biomaterials. So, many advantages, disadvantages of various materials. So, if you look at polymer, we are going to spend a lot of time later. We have natural polymers, we have synthetic polymers. Natural could be proteins like collagen, fibrinogen, soy protein, whereas you also have polysaccharides like hyaluronic acid, cellulose, chitin and so on, glucans. If you go to synthetic material, we have non-degradable and degradable. Non-degradable is like your polypropylene, polyethylene, polyacetate, polyurethane, polycarbonate, PVC, PMMA. Degradable, you can have PGA, PLA, polycaprolactone, polylactic acid, polyhydroxybutyrate, and then even aliphatic polyesters, so they all degrade nicely. So, advantages, disadvantages, they have sustainable production. So, we can manufacture them nicely using petroleum based raw materials, they are biodegradable, and they are biotech compatible. So, a lot of advantages. If you look at biopolymers, there are quite a lot of biopolymers, polysaccharide based biopolymers, protein based, then we have the synthetic semi bio-derived monomers, so polylactic acid, then produced by organism, polyhydroxyapatite, then you have the glucan based bacterial cellulose. So, we have extracted from biomass, obtained from bio-derived monomers or produced by organism. So, a huge number of biopolymers are now slowly coming. They can be nicely tailored. When I say tailored, we can change the molecular weight. If it is a bacterial based biopolymer, by modifying the fermentation condition, we should be able to tailor make the molecular weight of the polymer. We can blend it with synthetic polymer to achieve the desired properties, because biopolymers might not have the desired strength. So, we can use a synthetic polymer in addition to achieve the desired strength, and we will be able to use it for making different biomaterials of different size and shape. Okay. So, that is the advantage of bio based material. Okay. So, huge number of opportunities are there, especially for one to do research on bio based material, either animal origin, either plant based origin, okay, or monomers which are derived from biological raw materials. Okay. So, there is a lot of interest in bio based polymer systems. You need to do surface modification of any material, so that it becomes biocompatible, it does not cause any toxicity to the host system. So, the material should not be bioreactive, and so on. We will spend more time later. So, there are many physical and mechanical approaches for doing the surface modification. Even chemical treatment method, for example, if I want to make it very hydrophilic, I want to put in lot of hydroxy groups. So, I can modify the surface of a polymer to put more hydroxy group. Okay. For example, if it is too hydrophilic, I want to make it hydrophobic, I may reduce the hydroxyl groups that are present. If it is very okay, if there are too many positive charge, if it is very cationic, I want to make it neutral, I can put functional groups so that the charges are getting neutralized. So, a lot of chemical treatment approaches are there for surface. Then biological treatment, I can even immobilize cells, I can immobilize proteins, peptides. So, the surface becomes more biomimetic, surface becomes more biocompatible. So, a lot of work research possibilities are there, especially in the area of modifying the surfaces using biological. I can seed cells so that bacterial contamination does not happen. Okay. I can have some growth factors immobilized on this surface of the polymer, so that the surface acts as a very good scaffold for growing cells. So, again various opportunities are there for looking at surface modification of materials, either through physical, mechanical, chemical or biological method. There is a lot of interest nowadays on biological surface modification techniques. So, surface properties of material, when I say surface properties, surface is either hydrophilic or hydrophobic, surface is either ionic or neutral. Okay. So, we can look at surface charges, we can look at the surface morphology, we can look at whether the surface has pores, okay, whether we can look at what type of functional groups are present on the surfaces. So, different types of surface properties are available. We can use different instruments. We will talk about instrumental approaches later on, how to look at surfaces, how to look at charges on surfaces, how to look at surface morphologies, and all those we will be looking at as time goes on. So, the materials of course deteriorate with time. Materials deteriorate because presence of lot of enzymes in the a lot of body fluids that are present. Materials deteriorate because where it is located inside the body, bacterial contamination, bacterial growth, release of certain toxic material by the bacteria, all these can lead to deterioration of biomaterials. When we talk about deterioration, it is degradation, leaching out of monomers, leaching out of stabilizers and so on. If you are talking about metals, then of course we are going to have corrosion, polymers can have degradation, sometimes you can have calcification, in addition we can have oxidation, reduction, amidation. So many types of reactions are possible because body contains a lot of enzymes and proteins which can lead to these type of chemical reactions or biochemical reactions. Then we are having to have mechanical loading, especially if it is replacement of a bone, long bone segments, or replacement of different joints. Then we are going to have mechanical loading, mechanical wear and tear, leaching of certain metals from these joints. Okay. So, all those things are also possible, that also leads to deterioration and failure of the biomaterial. Okay. Then we can also have these combined or combinations of all these effects actually. So, there could be a slight deterioration. So, a coating which is present on a metal to prevent certain corrosion gets removed. So, the metal will start getting corroded over a period of time. So, we are talking in terms of combinations of deteriorations. We will talk about each one of them a little bit later on in detail also actually. Okay. So, how do we select materials? It's there is no single answer. Okay. In selecting, because as I said, some biomaterials are placed in the urinary region, some materials are placed in the blood region, some materials are placed as heart valve where they actively move continuously. So, some materials are like your urinary catheter are placed for only few hours, whereas if you look at cardiovascular stents, they are placed for many years. If you are looking at joints, they are supposed to last for the entire life. So, if time factor comes in, mechanical loading factor comes in, the location in the body comes in. So, there is no single answer for selecting a biomaterial. So, depending upon the application and duration, we need to have different criteria. So, we need to consider mechanical properties, we need to consider chemical properties, what type of biological effects that may take place, because we do not want any biological reactions taking place. We have to consider carcinogenicity, toxicity, is there any allergic reaction? For example, a chromium plate might not cause allergy to some patients, whereas a chromium may cause allergic reaction to some other patient. Okay. Is there any immunological effects? How do you fabricate? Is it easy to fabricate? How do you process the material? Is it easy to sterilize? Okay. Can we make hundreds of biomaterial? Oh, there is a spelling mistake here, it should be a good. So, can we keep on manufacturing in large scale with reproducible properties? So, all these also needs to be considered, because ultimately we are talking in terms of manufacturing and selling it. And then of course, cost benefit is very important. We have to consider is it cheap or it is very expensive. See, for Indian scenario, we have to consider how expensive is the biomaterial. Okay. Because India is a poor country and it is not so easy for everybody to afford biomaterials which are very expensive, unless you have say medical insurance. So, for example, your imported cardiovascular stent may cost a couple of lakhs, which drug eluting cardiovascular stent, whereas your ordinary bare metal stent may cost 1.5 lakhs, whereas if it is manufactured in India, it may be much less. So, the physicians have to give all the options to the patient so that they can select the biomaterial based on the cost benefit analysis. So, this goes for many of the products. Imported products may be expensive, Indian products may be cheaper, Indian products have equally good benefits, and that needs to be explained to the patients by the physician, so that the patient can make a cost benefit analysis. Some of the joints, hip joints may last much longer, several years, but it may be very expensive, whereas there could be some hip joints which are cheaper, which life may not be as much as those expensive ones. So, patients who do not have an active life can manage with those type of hip joints. So, we need to really educate the patient of different types of possibilities that are available, what are the cost of each one of them, and what type of situations are suitable for each one of the product. So, I think that sort of knowledge has to be imparted to the patient so that they can make a good selection based on many factors. So, these are some of the criteria for material selection. Okay. So, material properties, if you look, it is huge: compressive strength, tensile strength, bending strength. Of course, these properties are not necessary if you are going to have a passive biomaterial like okay, catheter or something, but these properties become important when you are talking about hip joint or bone replacement or even your heart valve. Coefficient of thermal expansion, if there are going to be any changes in the thermal coefficient of thermal conductivity, surface tension, hardness, density, hydrophilic, hydrophobic properties, water absorption, swelling, solubility, surface friction, creep, bonding properties. So, all these are very important which needs to be considered. Bonding comes in if when we are having two or different types of materials combined together. Okay, so, I have a ceramic combined with a polymer or a polymer with the metal, especially in your hip joint. So, there has to be a good bond between these two. So, in such situations we will have bonding properties to be considered. So, all these properties need not be considered for all biomaterials. So, we will be taking properties which are very specific for particular type of biomaterials and the application. Okay. One needs to consider also what is the interaction with the cells or the tissues with the biomaterial. Okay. So many factors we need to consider as we go along, and it gets very complicated because the biomaterial has to be implanted and placed inside the body for either a short period of time or for a very long period of time. Okay. Thank you very much, and we will continue in the next class.